Hello everyone and welcome to our 17th lecture. As you can see, I renamed them from lessons to lectures because, well, it's a bit more one-sided than a lesson would be, since the point of the lesson is that you ask the teacher and they help you out. In a lecture, usually it's present the topic and then the questions in the comments. So yeah, from now on my lessons will be lectures. So welcome to the second trigonometry lecture. The topic today is unit circle and trigonometry graphs. So last time we started talking more about the angles, like the angle between two triangle sides. Well, today we will learn the angle units. Firstly, of course. The first are degrees, not the temperature ones, but the angular ones. The unit marking is a tiny circle written like an exponent would be, although when you write too much, like after long writings, it ends up looking like an extra zero, so do be careful. But yes, each degree, so 1 degree, can further be divided into 60 minutes, marked with a symbol similar to an apostrophe. It's called a prime. Basically a small comma in the exponent position. And each minute into 60 seconds, so 1 degree is 3,600 seconds, where the marking for seconds is 2 primes. It is good to remember the name because it will come back several times in physics, chemistry, and maybe even in math. But yeah, back to the topic. I won't dive too deep into minutes and seconds. I'll just be writing degrees with a decimal place, as it will make calculating a lot easier and faster. Plus, after learning about them in like high school, I have not seen them once. So, degrees are the only thing that matters so far. If you ever go into something that demands such precision, you're gonna be working with these, but for us normal people, degrees are fine. The next thing to know about degrees is that if you take a random point at the end of the line, and then make a full circle back to the starting point, that would be 360 degrees, which hopefully you all know. This means that half a circle is 180 degrees, which is why the phrase something did a full 180 means that a thing we are talking about turned to face the opposite direction, aka back from where it was facing before. The other unit are radians, also marked with a rad, and sometimes just not marked at all, so written as a unitless number. Here the full circle is defined as 2 pi radians, meaning half a circle is 1 pi radians. To convert between the two, you would multiply the radians with 180 degrees divided by pi, or you would multiply the degrees by pi, divide by 180 degrees, and then get radians, because here, technically pi radians, and then here's the degrees, so these two would cancel out, so you just get a giant number. Don't worry, we'll solve a few examples later. But this means that 1 radian would be equal to circa 57.3 degrees, or slightly less than 1/6 of a full circle. But that's not important, since you can always solve it for yourself with these two formulas. Here is a circle with painfully handwritten angles. So assuming we start along the thick horizontal line facing right, we have first a 0 degree angle, so between this line and this line, so itself. This is a 0 degree or a 0 radian angle. Then we start moving counterclockwise. When we reach the top of the circle, the angle between the vertical and the horizontal line is 90 degrees, or pi halves radians. When we reach the other end, so we have a horizontal line only, that is 180 degrees, or pi radians. When we continue forward and reach the bottom, we have a big, very big theta that encompasses 270 degrees, or 3/2 pi radians. And when we complete the circle, the angle is 2 pi, or 360 degrees. Hopefully, with this we finally see why the DAG setting was so important in the last lesson. As we told the calculator, we are inserting degrees. You can try to put in the radians on R setting to test this for yourself, because doing something yourself is one of the best ways of learning something. Also, while we're at it, I think it's time to mention that anytime you see a pi in formulas, like formula for circumference of the circle, sure, pi is defined as the ratio between the circumference and the diameter, so the around and the r, the whole thingy. But if you think about it, if you take the diameter, so 2 times radius, so the horizontal line from one point to the other, so 2 times radius, of course, and then spin it over the center point for 180 degrees, so both ends end up on the opposite side, it draws the full circle, so the circumference if you're looking at the points only. It's just something interesting to note here, might help you understand some other concepts as well, so I throw it in just in case. But yes, for examples, what is 45 degrees in radians? Let's remember the formula. If 2 pi is 360 degrees, then we set it as a ratio, so our answer in radians is marked as x, and we get an equation of x over pi, so radians cancel out, and 45 degrees over 180 degrees, because 2 pi and 362 cancels out. But yeah, this is the formula where the units cancel out. We carry the pi to the right side and simplify the fraction. We know that 45 is a half of 90, and 180 is 2 times 90, so we get 1/4 pi. And our x is equal to pi fourths. And that is our result. The next topic is the unit circle. It is a circle with a radius of 1, so exactly 1 unit. Basically, we assign the length of 1 unit to it to make calculations easier. Here we will be moving a line around, and the angle between the line and the starting point will be theta. The points that the line, let's call it the hand, touches on the circumference will have their coordinates determined by the trigonometric functions. So you see this is a right triangle, this is a 90-degree angle. Sine is the opposite divided by hypotenuse. Hypotenuse is the radius, and it's equal to 1. So our coordinate would just be sine theta as the y-coordinate. Same thing for cosine, which is the x-coordinate. Basically, all that is important to know is that up and down will be the results of sine, and left and right will be the results of cosine. So we see that our angles, while they're less than 90 degrees, so in this area, or above 270 degrees, so here, the x-coordinate or cosine of theta will be positive. For angles between 90 and 270, so on the entire left side, cosine will be negative. And at exactly 90 and 270, it will be a 0. As for y-coordinates, aka sine of theta, between 0 and 180, it is positive, and between 180 and 360, it's negative. At 180 and 360, or 0, it's 0. So cosine of 0 is 1, and sine of 0 is 0, for example. And now that we have visualized sine and cosine, what about tangent? That's also the third important function. Well, there's two ways. Essentially the same thing, but one is that we extend the hand and draw a vertical tangent, the important word here, tangent, to the circle, which touches it at the point 1, 0, like in the picture on the left, so here. And then you connect these two lines, and the length between the intersection and this is the length of the tangent. The second picture, the second way, is that you draw a tangent perpendicular to the hand, out from the point here, or at a 90-degree angle from the point that the hand is pointing to, down towards x-axis. So if it was on the left, it would point down to the left. Since it's on the right, it points to the right. And the length here is the length, or the tangent of x, or theta. This is done so that the adjacent side is being set up as radius. So you can see theta is here, and the adjacent side next to it becomes the radius. Before that, that was still the adjacent one, but the hypotenuse was the radius. And since hypotenuse is in the denominator in sine and cosine, it made sense that we set it as 1. Here, tangent has opposite over adjacent, so the goal is that our adjacent side becomes 1. You can use either option, whichever one is easier for you to remember. I maybe prefer the first one, but that's just personal preference, because, I don't know, my personal preference, I guess. So for our first problem, we need to find a point on the unit circle where the described angle, that is described by an angle of 60 degrees. So to solve it, we can draw our unit circle to help us, or at least sketch it so we know roughly where it is. Or you can just use a calculator. For x-coordinate, we will use the blue circled cosine of 60 degrees, and for y, a red circled sine of 60 degrees. Make sure that the part marked with yellow is not there, so that we set the units to degrees. Otherwise, you must convert 60 degrees into radians, and I'm pretty sure we would all rather just use degrees. Oh, and since I forgot in my last video to change it, you need to press the drg. So you see this function above the answer. For this calculator, you use shift and then answer, and that would automatically use drg. And you click that until this is gone, or says deg. Basically, drg changes the units I don't even know what it stands for, to be honest. I might look it up. So, when we put them in the calculator at the right units, we get 0.5 for the x and 0.866 for y. In fraction form, they are 1/2 and a square root of 3/2. How did I know this so fast? Well, there are tables for common angles like 30, 45, 60, and 90 degrees, etc. Or in radians, they are pi sixth, so a sixth of a pi, a fourth of a pi, a third of a pi, and half a pi, respectively. Sure, there are other angles too, but I'll show you the image after I'm done, so you can see how it works. Let's start with sine. So here are listed all the most common angles between 0 and pi halves in degrees and radians. Now let's start listing. So sine of 0 is 0. So 0 degrees, 0 answer. As we move up, we get a sine of 30 degrees, which is 1/2. You can do this with the calculator along to see the numbers for yourself. Sine of 45 degrees is square root of 2 divided by 2. I gotta mention this though. More often you're gonna see 1 divided by square root of 2, but I use this for a purpose, which you will see in just a little bit. So don't worry if you see different result. I just factorized it. They didn't. So basically I multiplied both sides with a square root of 2, although I think I explained this later on in the video as well, so let me not get ahead of myself. So the sine of 60 degrees is a square root of 3 divided by 2, as we remember from the exercise. And sine of 90 degrees is 1, so the top of the circle. I saw a pattern that makes this super easy to remember, and it is that all of them are halves. But numerator is a square root where each higher angle increases it by 1. So square root of 0, square root of 1, square root of 2, square root of 3, and square root of 4. Square root of 0 divided by 2, square root of 0 is 0, divided by 2 is still 0. Square root of 1 divided by 2 is 1 divided by 2, because square root doesn't change anything here. Square root of 2 and square root of 3 stay the same here. And square root of 4 is equal to 2, and 2 divided by 2 is 1. So this way helped me memorize these tables much faster and easier. Hopefully it does to you too, otherwise you might just have to purely remember it. Now, if you imagine a unit circle, we know that we start at x is 1 and y is 0, where x decreases as we go, as theta increases, and y increases as theta increases, between 0 and 90, of course. That means that cosine, which represents x, must be decreasing. So let's see the values and then check another pattern. Cosine of 0 is 1, as we remember from the circle. Then we have 30 degrees. If we enter that in, we get square root of 3 divided by 2, which equals to 0.866, etc. So this result. After that, we have 45 degrees, or a halfway point between 0 and 90. That's where the value of square root of 2 is divided by 2. By now you probably see the pattern that cosine will have the inverted order that sine had in the table, like so. So technically, if you remember the unit circle, where the angle is placed, the definition of trig functions and that the values of trig functions are, the values of the trig functions of the angles that are in form of a square root of some n divided by 2, that n changes by 1 from 0 to 1. This is complicated, but just a summary of the entire thing. Sure, you don't technically need to remember the table, but I'm pretty sure most teachers will want you to know it if you can't use a calculator on your exams. Basically, they're all halves, sine increases, cosine decreases, and the increment is in the x under the square here on top. You kind of see the pattern here, hopefully. Also, it's important to note that sometimes the 45 degrees value, so square root of 2 divided by 2, as I said before, can be written as 1 divided by square root of 2, since that is the unfactorized value. I taught you that when you have a radical in the denominator, you try to get rid of it by multiplying both sides with that radical. Lastly, for tangent, because I hope you memorize this, the values will be slightly different, but there's still a certain rule that can be found. Tangent of 0 is 0, because if we look at this image, we see that if our angle were 0, the distance between the line and the x-axis would be 0. Then we have 30 degrees. Since the extended hand will reach further up, if it wants to get above the x equals 1 point, y will be slightly higher than that of sine. or cosine or whatever, and that higher value is 1 divided by a square root of 3. We will get to why that is in just a little bit, I think in like 5 slides, or square root of 3 divided by 3. I'll leave this unfactorized form purely because I want to show a property easier. Then we have 45 degrees. Now, if you know triangles and that you have a right triangle, you have one angle that is 90 degrees. That means that the sum of the other two is 90. But if one is 45 out of them, that makes the other one 45 as well. Therefore, the two sides, other than the hypotenuse of course, must be the same length. Meaning that with tangent, where we have fixed the adjacent side as 1, this triangle rule makes the opposite, so the result of tangent of 45 degrees, 1 as well. So the result is 1. Next is 60 degrees. This one equals to square root of 3. I'm not going to be bothering you with the math because you can do the Pythagorean theorem or... wait, we haven't covered those equations yet. We do that next time, yes. But yes, and when we get to 90 degrees, there's no way to draw a straight line as a tangent to the circle at that point, so that it would intersect the x-axis and the hand, which goes straight up, because at 90 degrees the lines are parallel. Therefore, the tangent of 90 degrees becomes undefined, as the length of the line would be infinite, and infinity is not a number but a concept. In this case, it would be impossible to define the length, since they would not meet even in infinity. Truly a sad love story. Here we can kind of see the pattern, and that is that 1 is fixed at 45 degrees, but each angle step we make away is the reciprocal value of the 1 if we step the other way. So the value of tangent 30 degrees is reciprocal value of tangent of 60 degrees. And we hopefully know that reciprocal means 1 divided by that number. So if we divide this 1 by this number, we get this. Kind of makes sense, you know, because undefined 1 divided by 0 becomes undefined. So sure, there's also a table for cotangent, which is just mirrored tangent, just like the sine and cosine had it. And there's tables for other functions and higher angles, but I won't bother you with those as that is truly not the very basics I'm here to present. And as promised, here are the unit circles with all significant angles marked. One with radians, by math is fun.com, right here. And the other one with both angle units, but more color-coded values, from easy7s.com. Short shout out to these two sites for having amazing unit circles done. Hopefully they can help you understand this slightly better, so we can move on to one equation that I must show you today. Also, before I go ahead, in these circles you can see that 0 plus 30 degrees, so up here, will have the same values as 180 minus 30 degrees, well, with the exception of x being the negative. So for solving the angles with this table, you need to determine in which quadrant the value lies. Meaning the best way is to sketch the unit circle, mark the 90, 180, 270 and 360 degrees, then roughly mark where the given angle is. So then you know whether the x and y are positive table value or negative table value. Usually my best suggestion to help you would be that you look what the angle is from the horizontal lines, so from 0 or from pi. That way you can predict the value with the table and then just set the signs depending on the quadrant. So as we see on the right, 150 degrees is in the second quadrant right here, this line. So that is 30 degrees from horizontal line. So I subtracted from the closest angle, which is either 180 or 0 degrees, and I got 180 minus 150, and it's 30. If I look into the table, the values for 30 degrees are sine 1/2, so the y value, and cosine square root of 3/2. So I mark them as y and x respectively. Now for the signs. Since the second quadrant is left, the x must be negative. And because the second quadrant is up, the y is positive. And voila, we've solved this. Next time we will learn how to work with negative angles, which will allow you to set better rules for these situations as well. So don't worry if you didn't quite get y minus and y plus. Now for our important formula for today. So we know that sine is opposite divided by hypotenuse, and cosine is adjacent divided by hypotenuse. I should be saying side after each one, but I'm shortening it so it's easier to comprehend. But tangent is defined as opposite over adjacent. And here I can kind of see something. So let's divide here. in formula for tangent, both sides with hypotenuse. So the length of hypotenuse. Since this is a fraction, just like with equations, we can do this. This will be done a lot more in physics and in actually future lessons in math to help us derive formulas. So we divide both sides. So we divide the opposite side with hypotenuse and the adjacent side with hypotenuse. And we see we get the two familiar formulas I mentioned just a bit before. Opposite over hypotenuse is sine, and adjacent over hypotenuse is cosine. This is another formula for tangent, so dividing sine of x with cosine of x will give you tangent of x. It is useful in equations later on, where you have two trigonometric functions and you try to get one or just to simplify. Here I could give you the homework to go back to the tables and check if the quotient of the values for sine and cosine at the same angle gives us the tangent for that angle. But I'm sure you're curious enough for yourself that you're gonna go do this. Oh, and the part where we divide by 0 also explains the end result. With this equation, you can finally understand this amazing meme where a sine of gerine and cosine of gerine gives us a tan gerine. Now I'll pass the torch for a bit to Future Next, doing this part in PhET, the link is right here, which is an amazing website for science simulations from math, physics, chemistry. I will show you where does this unit circle come in handy. But yeah, I'm just gonna show you stuff about the graphs and the unit circle. So here is the link, and I'll see you in a bit. Thank you for the introduction, Pass Next. So here I'll take over. This is PhET. This is how the website looks like. Oops. This is how the website looks like. There's like physics, math, statistics, chemistry, earth, space, biology. Oh, they added biology, that's cool. And this is a lesson called Trig Tour. Oh, it's cut out slightly. But here I basically can choose which graph I'm gonna be looking at. So I'm gonna be looking at the x-coordinate or cosine first. So you can see that I can drag this red ball around and it changes the x and the y coordinate. Here on the left we have the angle listed, the coordinates, and the formula calculating it. We can choose radians or degrees. And at the same time we have a graph down here. So you can see that as I'm adjusting the position of the point, the x-coordinate is changing, while the graph is drawing its respective value. So just like this. Now I'm gonna switch to sine and start in the starting position to explain how this graph looks like. So imagine there's a light on the left, so a giant flashlight shining towards the right. And this point is just a random ball, and we're observing the shadow here, the position of the shadow of the ball on the wall behind it. So a lamp, a ball that's moving in circles here, and the wall. And this graph is the projection of height over time. So as I'm spinning this, you can see that the shadow is also moving up. But once this one starts to decrease, the height will also be decreasing there. And it goes into minus, and then back into plus. So for sine, this looks like a projection from left to right or right to left. For cosine is from up to down, as you can see that, oh, I lagged. As it's here, this is top and this is bottom. So this value here is this value here, and this value here is this value here. As for tangent, well, this one takes this straight line value. So if I drag this one up here, this one is gonna go extended to this point. And then if I keep it moving, you see this one is getting launched into heavens. And when I tap 90 degrees, it goes plus minus infinity because, well, they're parallel. And once I return it here, it finds a line right here that it goes in this graph in negative because the slope is negative down here. Or, sorry, the distance is here to here, or from here to here. And since it's on the left, it's negative. And we just keep repeating this. Here's also the special angles. So the 0 degrees, let me go back to sine. 0 degrees, 30 degrees. Oh, wait, hold up. We're gonna reset that because that was 390. So 30 degrees, 45, 60, 90, 120, 135, 150, 180, 210, 225, 240, 270, 300, 315, 330, and 360. We can keep spinning these, and we see that even as the angle increases, these values keep following. They keep following the table that we've already shown. So hopefully this site helps you out learning on your own or just following along. And yeah, back to you as next in the PowerPoint. Thank you for this informative explanation, future next. Now let's go into the graphs. First I'll show you the ones that we have covered so that you have seen in PhET. Then I'll show you for cotangent. After that I'll show you the inverses as well. And I'll tell you the main properties with the big three. The rest I'll just show you how they look like compared to the inverses. Now usually the functions have theta or other Greek letters, but as I said last time, I'll use x sometimes, most commonly in graph terms, since I did figure out how to do that, never mind. But yes, graphs are usually for sine and cosine and stuff. They're usually drawn as a horizontal line that comes from a vertical line, marked only with the maximum and the minimum value. These values are called amplitudes, so the maximum deviations from the midline. In physics, we will mark them as plus a0 for maximum and minus a0 for minimum, where a0 just refers to the amplitude. For instance, v0 for speed of a pendulum, or s0 for how far it swings out, etc. Plus and minus just refers to the relative directions, which you decide when you're observing the system. But due to Desmos being Desmos, I'll use a coordinate system to show these graphs. So as I said, I did manage to change the units into pi. So here working with radians to show the properties, but I'll also attach a degree one so that you can have both here. But from that forward today, I'll be using the radians as units since they're more commonly worked with here. The one in radians, so the bottom one, has 2 full circles, as you can see, up to 4 pi. So it's easier to show the properties, while the degree one is just to show the change of the y-coordinate. So the top one is in the degrees and the bottom one is in radians. We see that the radians graph has a sort of pattern. It goes up and down and up and down. And we can find a part that if we loop it and repeat it endlessly, we get a sine graph. So I enclose it in blue brackets, so between 0 and 2 pi. We say that this part repeats periodically, and sine graph repeats every 2 pi periods. So you have a number like 74.3 pi, and you need to know the value, like the exact pi value or the coordinates in the unit circle. You just subtract 2 pi until the number you have is between 0 and 2 pi. And then you put that into the graph. So here that would be 74 minus 2 minus 2 minus 2 minus 2 minus 2. You end up with 0.3 pi, which is slightly to the right from the start, so roughly where the red dashed line is. This is a horrible sketch. Ignore me. This is probably even more incorrect than if I actually did the math here. It was just an example that I came up last second with. Yes, our domain here is real numbers, so we can put any x or theta in this axis here. And our codomain is numbers between -1 and 1. And here I wrote it down periodically, so periodicity is the property of the function that states at what point it repeats itself, so the length of the quote-unquote loop. So you can see here, we find the smallest element that we can endlessly loop it to get the function. Length of the interval it's called period. I may have translated this all wrong, that's why I've been stuttering a bit. So do fact check me on this, but definitely has at least a similar way of being named. As for the amplitude, it's marked with a capital A or A0 in general context, and it's found before having the sign writing something like this. So the amplitude is determined by this A that's multiplied to sine. That sine just has this wavy graph where it starts at 0, goes up, goes down, goes up, goes down, goes up, basically reaching peaks at multiples. Yeah, basically every 2 pi it repeats, so 3 pi, 4 pi, and that's 2 whole repetitions. That's the most important part about this graph then. Same properties are here for cosine, except we see it as it starts from the value 1. And well, that's about it. It's basically sine graph moved to the left for pi halves. Domain is all real numbers, codomain is the same, period is the same, and formula is the same. Now tangent, this one is slightly different. Remember the undefined values at pi halves, so 90 degrees? Well, here we see them as dashed blue lines. So our graph for tangent has different properties. For domain, the x is element of real numbers. where x must not equal to pi halves plus n times pi, which basically means that the simplified fraction that ends up as the odd number pi divided by half are the vertical asymptote positions. So anytime you cancel out a fraction, it still has a half on the bottom. That's the asymptote here, basically. We can see that the period here is only 1 pi, so between pi halves and 3 pi halves and whatever. So this period also applies to asymptotes as well as the properties. The codomain is all real numbers, as we get that from all negative infinity to positive infinity. And well, that's about it too. I'll now show you the graphs for cotangent and the inverse functions without going into properties. So cotangent is just like tangent, where only whole pi values, so n times pi, where n is whole number, is the formula for vertical asymptotes. So again, just moved slightly to the left and mirrored. The inverse function of sine is the arcsin. Takes such shape. This is of course stretched to show roughly where it starts and ends. But this is the entirety of the function, with the inverse point being in 0, 0. This is it, from -1 minus pi halves to 1 pi halves. Arcos cosine is mirrored across y-axis, I'm pretty sure, and then moved up. Well, technically they're each a mirror over y equals x line of the respective trigonometric functions, but yeah, you're not gonna see much of this one anytime soon, probably. And I gotta say, out of all the inverse functions, this one just seems the nicest to me. Nice, smooth curves, and contained between two asymptotes. So basically we took one of the infinite segments, mirrored it over y equals x, and got this beauty right here. So this is it. Here is the mini test, which I wish you best of luck solving it. It's not really that hard though. Now, last week I posted a short video as I'm experimenting with different styles of educational content, and it seems like you guys really liked it. I also appreciate all the feedback from editing tips to video duration suggestions. So if you made it this far, please comment what you would like to see me do next in those shorter videos. And if you have any tips and feedback, I'm more than happy to hear it. This is it. Thank you so much for tuning in today, and I'll see you all on our next quest. Bye!